No, I should stand somewhere close there. Right? Yeah, for that, but you're using the microphone because of the people.
Yeah, you have to. That's why you have to stand there.
So this one.
That's the microphone.
Yeah. If I will fall from the stairs, I will continue. Do not worry.
Welcome back, everyone. We start this symbiotic systems session. Right now we have Yaroslav Mek with this talk. So we will let you know whenever time is up.
Should I wait for people?
Yeah, let's just wait for a couple of minutes.
I'll start my timer.
When the start is not the start.
We ready? Most of us? Good. Go ahead.
Thank you very much. So I was told I should stand here. I hope I will not fall down. So now, finally, I will talk about my favorite subject, which are symbiotic stars. And I titled this "When a PN isn't a PN," and you will find out why at some of the later slides. But first, let me just recap what symbiotic stars are, despite they were mentioned already a bit. So this is the most important slide for you to take home, about the symbiotic stars. So these are interacting binaries of a red giant donor and a white dwarf or neutron star accretor. Typically, the red giant is a M-type. There are some of the we call yellow symbiotic star with K giants. And then you have a lot of stuff going on because of the interaction. You have a nebular emission, you have dust. And also important about symbiotic stars, and that's important for the search, and I will be talking about searching for symbiotic stars as well, is that these are very wide systems on the orbital periods of hundreds of days up to tens of years. And they're complex. Complex environment was already shown Araquarry, so I'm not showing, typically I'm showing Araquarry in my talks as an example of complex environment, because that's one of the closest. I'm not, because we will be hearing for an hour about Araquarry during this session. They have complex spectra, complex variability. I will be ignoring variability in this talk because I don't have time to discuss that. But I will show you some of the symbiotic spectra. These are optical spectra. These are those well-behaving symbiotic stars where you see the red giants continuum, and you see these strong emission lines of hydrogen, helium, and highly ionized emission lines of whatever. These are less well-behaving symbiotic stars, but still nice. These we call D-type symbiotic stars, dusty types, in contrast with stellar-type symbiotic stars. Because you have a lot of dust that is produced by the Myra donor, you don't see any continuum, but you see plenty of emission lines. And for you, working with PNs, this is really something what looks like the PN in the optical spectrum. So I will be talking about the search for symbiotic stars, and especially with Gaia data. And the motivation is here on this slide. These are predictions of the numbers of symbiotic stars in our galaxy, which range from 1,000 to 400,000. These are overestimated, but anyway, they were published as that. But anyway, if you compare that with observed numbers, they are much higher. So this is the motivation. If you will read a paper that is searching for symbiotic stars or trying to search for symbiotic stars, the first sentence is like, there is a discrepancy between the observed number and the predicted number, which is true. So then people use multiple ways how to search for symbiotic stars with the large data sets we have with machine learning and so on. But before I will talk a bit about how this is done with Gaia, I will shortly introduce the general ways how it is done. So the very traditional way is to select the symbiotic candidates from narrowband photometric surveys, especially. So you are searching for H-alpha emitters that are red, let's say, and then you do the follow-up for that. There are problems with this method in sense of contamination, and I will speak a little bit about contamination soon, because you have a lot of false positives. So the only way how to then confirm is to do the spectroscopic follow-up. But there are also other approaches people were exploring, trying to search for example, for sources which reminds red giant but have some UV excess. So with combination with UV data, infrared, or some X-ray motivated surveys. And there are also very recent, let's say, the efforts to explore the spectroscopic datasets from Gala and Lamos, because then you have the spectroscopic follow-up at the very beginning already. So you don't need to do that because you start with the spectroscopic data. But it's not easy, and it's not producing that many symbiotic stars as people thought. And then, of course, we have Gaia, so people try to use Gaia data to get something out of that. The thing that you need to be aware when you are searching for symbiotic stars is that there is a lot of things that can remind a symbiotic star depending on the data, so the way how you are looking at that particular object. If you have a spectrum, if you have just photometry, if you have just X-ray data or whatever. And this actually is a symbiotic star there in the middle. That's Mira pulsator. So that's not a contaminant, that's a symbiotic star. And I listed some of them here, and I will talk especially here about planetary nebulae, because that's most of the talks are on. So actually, there is a lot of known symbiotics that were initially classified as planetary nebulae. The reason is that when these were done from the objective prism surveys, for example, there was a very faint continuum emission line, so it reminded something like a PN. Because planetary nebulae, as we know, there are strong emission lines, and as you saw on my slide at the beginning there, their spectra can be very similar to these dusty type symbiotic stars. And actually, if you have this young, dense, compact, and not resolved planetary nebulae, it can be very difficult to distinguish, even with nice spectroscopic follow-up. And also, some true planetary nebulae are suggested to have symbiotic cores, and these are the two examples where it's not visible because of the dust, but there are works suggesting that inside there somewhere you have a symbiotic star. There are ways how, if you have the follow-up, how you can try to distinguish based on spectroscopy symbiotic stars from planetary nebulae. For example, these are O3 diagnostic diagrams, and you see that the planetary nebulae lives in a bit different region of the diagram as symbiotic stars. But the thing is that for this kind of work, you need to have spectroscopy with a reasonable high resolution to actually be able to measure the fluxes of these emission lines. So here again, on that topic of these things being similar, you have two PNs and one symbiotic star on this figure, and you see that on the first look they can look similar, but then if you measure the fluxes, you can distinguish. The problem is, and now I'm getting to the Gaia part, is that if you have a Gaia BPRP spectroscopy, for example, which is very low resolution, I am not able to distinguish between planetary nebulae and symbiotic stars. And this image is showing in blue 2 symbiotic stars and 3 planetary nebulae. And you see that they're low resolution, the super low resolution Gaia spectra, but people are using that for searching for symbiotics. Or classifying emission line stars, they look exactly the same. So then it's very hard just based on this data set. And that's something that is also a take-home message from my talk, as you will see, is that if you have a very limited information, it's very hard. So you need to really collect as much information as possible. There are other ways, and I'm showing here 3 diagrams of the same kind of thing. So these are infrared, near-infrared color curve diagrams, and you see that symbiotic stars here live also in this diagram in a bit different region. But again, the thing is that, for example, if you just take the Gaia data and not infrared, then you don't have this information. So you need to be careful with that. And Gaia itself, Gaia DR3 itself, included 2 products that are relevant here. First of all, it included variable star classification. That was done mostly on the photometric data. And the goal was to use machine learning to classify variable stars in Gaia data into 35 types and subtypes, including symbiotic stars, which is reasonable to one extent because symbiotic stars are variable, and also Gaia sees them as variable. Here is just an HR diagram of all these classes. That this is the DR2 actually figure, but you see that the variable types are populating the whole HR diagram. But given that the classification here was based on Gaia light curves, and like it's more complicated than that, but let's say the position in the color magnitude diagram is similar to one you see, then the problem here was with the contamination by single pulsating giants. I will not talk more. I have some extra slides. If you're interested, then in discussion we can talk about that. The more interesting part was the emission line star classification, because symbiotic stars are emission line stars. And Gaia DR3 included emission line object classification for 57,000 objects for 6 classes. And if you will take a look on those classes, you will not find symbiotic stars there. There was no symbiotic class. So by definition, all symbiotic stars are misclassified. And actually, there is a large number of non-symbiotic stars included, misclassified because there is no class for that. And most of them as T Tauri stars, which are young stellar objects, which can have a red continuum and emission line. So they will look very similar to symbiotic stars in low resolution. 24, especially these D-type symbiotic stars, were misclassified as planetary nebulae. And that's the reason why I called the title was, when a PN isn't a PN, because there is a lot of PN in symbiotic, in Gaia DR3 sample that are not PNs. And 5 were more massive AEB stars, but they're all misclassified. So then we came with a kind of different approach how to do that, because first of all, we realized that most of the known symbiotic stars were included in what is called the specific object studies of the variability, and especially focus on long period variables, because that's what you see in symbiotic stars is either because of the orbital motion or pulsations, but this is what you would call long period variability. And those, given how they were selected, they already have the correct position in the color magnitude diagram, so they lie among the red giants. But we combine this variability information with the information about the emission lines. And what you see here, this is for the known sample, for known symbiotic stars. This is pseudo-equivalent width of H alpha as measured by Gaia. So this is something which is in the Gaia catalog. And you see that all the values are negative, which means that Gaia sees emission for symbiotic stars in the datasets. We included some other information because we have this option that we can use something else than Gaia data. Gaia DR3 or Gaia DPAC cannot use anything that is not Gaia for classification. I was able to do that, so we included TUMAS information, so infrared information. And just a side note is that we limited ourselves to pretty bright objects. So this work actually can be extended to something fainter, but then the data from Gaia can be not reliable and so on. And we wanted to do the follow-up for all the objects. We did some effort to eliminate from our sample the pulsating and late type contaminants, because we found out that these very late type stars, because of the molecular bands in the low resolution, can look like H alpha emitters, but it's just because at that position you have bands on the both sides. So the good way we found that you can actually distinguish between this MIRAs and semi-regular pulsators is to take a look at the error of the H alpha that is reported, because those that seems to have H alpha in emission but measured with the 400% error, that's MIRAS. So it's a way how to find MIRAS from spectroscopy without having any photometric information. Anyway, then we did some tests with the emission line stars list, and we ended up having a sample of stars selected from the LPD catalog with emission. It was the golden sample. We had 3 levels. But the golden sample has 64 sources. We all observed with spectroscopy, 94% had H alpha in emission, and 80% showed M-type continuum, so which is something what we were looking for. On top of that, we had a few hundred less promising candidates. But anyway, with this work, we ended up with 60 new symbiotic stars, including 2 carbon symbiotic stars. And on the last slide, in my last minute, we also tried to use this misclassification of planetary nebulae to search for D-type symbiotic stars, because the previous way is not very good for D-type symbiotic stars. It worked for S-type symbiotic stars, but not for D-types. So there is 273 planetary nebulae in the DR3 classification. Out of that, there is this number of either planetary nebulae or symbiotic stars. as miscalculated, plus the 14 in LMC, and some are already known as Wolf-Rayet stars, CVs, YSOs. So at the end, from this list, there is 74 sources which are unknown. 49 has BPRP spectra available, and only 14 out of that show emission. The other are trash. And out of these 14 planetary nebulae in Gaia DR3, we observed all but 3, I think, at this point. And we found out that 8 are likely new D-type symbiotic systems. 1 is nice S-type symbiotic star, 1 probably polar, and 1 is PN. And with that, I will leave you with my summary, and we'll take questions. Thank you.
Thank you very much. In spite of all the color diagrams, the true observational way to tell symbiotic stars is by the photospheric molecular bands. That's the only type of way. Most importantly, theoretically, after Buczynski and Rudek, they are different from planetary nebulae because symbiotic stars are not evolving. The nuclear burning rate is lower than the mass transfer rate. Whereas in the planetary nebulae, the nuclear burning rate is burning its own hydrogen atmosphere. So that is how you really distinguish the two classes. Observationally, it's very difficult to separate them.
I would be very scared to say that symbiotic stars are not evolving. That would depend on the time scale, I think. But yeah, sure. But we need to live with the observations we have. So I'm not saying that infrared color diagrams are the proof of symbiotic nature. It's the good way how to select the candidates. But then I think the main observational way today is to do the optical follow-up or infrared, but optical works. Because when you saw the spectra at the beginning and you see this red giant, which is a cool star with iron 16 emission, that's not this cool guy, doing that. So.
Yeah, just a question really. Nice presentation. Nice to see M29 and then Menzel 3 in your list. So did you check hash for the string symbiotic star candidates?
So yes, if
there are 49
yes,
there.
yes. If you will open my database of symbiotic variables, those from your database that are mentioned as symbiotics are included as candidates. If they have spectra, for example, and the spectra are symbiotic, then they are even among confirmed. But I think that you have some symbiotics among, for example, just emission line stars. But my kind of politics for new online database of symbiotic variables was that I am not including things that I have no reference for. So if you have not said this is a symbiotic star, but I know, I will first, analyze the object, publish a paper or something, and then I can reference to that and include that in. But all the symbiotic ones are included, yes.
So yeah, just a quick comment and question. No one yet, I think, in the meeting so far has mentioned SphereX as a potential really great resource, especially for pursuing the near infrared components of these. Are you expecting any emission lines that might be diagnostic in the near infrared that SphereX can help?
Nobody ever tried to do that in infrared. The one thing I would be worried about is that these emission lines are nebular, and it will go more to red. You start to be super much dominated by the red giant. So those lines can be pretty faint. If I can then show you, for example, even this Gaia RVS spectrum, there is just a very hint of emission there for non-symbiotic stars, but they are already so much dominated by the giant, and this is something like 8,300 whatever angstroms. It's so much dominated by the giant that this symbiotic phenomenon is not that basic. In some systems, I have nice K-band spectra, for example, and yes, there you see nice emissions. But nobody ever tried to do any diagnostics for that.
We thank Yaroslav again, and please save your questions for the discussion. Next speaker is Pedro Pablo Campo.
Okay. Good morning, everyone. Thanks to the organizers for accepting my contribution. And before starting, I must say that I come from a different background than most of you, because I've dedicated myself to the calculation of binary star orbits and celestial mechanics. So I hope you don't find this very boring. And what I'm going to talk is about two systems, Myra and Araquari. And we have calculated the orbits for those systems. So I'm going to start with an introduction to the problem. Then I'm going to speak about the observations that we have of these systems. A small part about the program that we use to calculate these orbits, and finally the results that we get. So for the introduction, I don't need to remind you that binary stars are one of the main origins of these asymmetric planetary nebulas. So it's very important to calculate their orbits in order to understand their dynamical evolution and the shapes that these planetary nebulas may achieve. But to determine these orbits, we need accurate measurements. And in order to get these accurate measurements, we need to use high-resolution techniques, like, for example, interferometers such as ALMA. And for this observation, for these orbits, we have used ALMA observations, among others in the literature, to calculate the orbits using our own software of orbit determination. So why these stars? Well, why we calculated these stars? Well, in the first place, because we have the observations, and in the second place, because the existing orbits for these systems are not working very well with these last observations. So for Myra, we have this previous orbit, is a somewhat old orbit from 2001, with a period of almost 500 years. But if we see this table, I hope it's not too much numbers, we can see here in the first two columns the epoch of the observation in Julian years or Michelin years. The following columns are the observed angle of position and the calculated angle of position, and the residual between the observation and the calculation. And the next columns are the observed separation and the calculated separation. And if we look at the residuals of this separation, we can see that we have a negative trend that indicates systematic error in the orbit that we have here. So this merits a revision of the orbit. In the case of Araquari, the residuals of the separation are affectable, but the residuals of the position angle, we can see that we have large errors that for high-resolution techniques like this are not very good. And for this orbit, for this star, we also have a spectroscopic orbit. In the 2009, we have this orbit by Gromadki and Nikolajewska, which has a period of around 43 years, if I remember correctly. But as we can see, we have an eccentricity for this orbit of 0.25, while for the visual orbit, we have an eccentricity of 0.45. So we have here some disagreement between the two types of orbits. Well, now for the observations, for Myra, we have loads of observations. We have about 100 observations in the literature that we got from this catalog, Sidonie for the visual observations, and the fourth interferometric catalog for the high resolution observation. But also we use observations made by ALMA from our own team, as you can see here, and others that we found in the ALMA archive. These ALMA observations are not incorporated in the core catalog because this catalog is mostly from optical observations, optical and infrared observations. For our query, we can see them more in detail because we have much less observations. We have an old observation from 1983 by Hege et al. That we suspect that is false positive because this observation gives very large residuals with any of the solutions that we tried. So we suspect that this yes, they didn't observe really the secondary component. Then we have an observations from 1996 by Hollis et al. Using the VLA continuum, and then BLT observations from 2014. And from 2017, we have several observations made by our team with ALMA. Here we have the last observations, the last observation by ALMA. We have here the star, this is the jet, and these are the positions of the other 4 ALMA observations that we have superimposed to the image. And now a small part about the program that we use, that we call it Orbitas, which is orbits in Spanish. And it's a software that we developed in Python, and it has 4 functionalities to work with mainly visual binaries, meaning binaries that we can resolve, but also some functionalities to work with spectroscopic orbits. The functionalities are the orbit calculation, ephemeris calculation, optimization of the orbit, and graphical representation. I'm going only to speak a little about this and this. The other are standard. So the method used for the orbit calculation is the method of Tocco, which was my PhD supervisor. It's an analytical method to obtain the orbit of a visual binary using 3 observations, 3 real observations or virtual observations. You can use 3 points through which you want the orbit to pass. So for the determination of the orbit, what we do is study a function. This function maps this variable, which is the difference between the eccentric anomalies of the third observation and the first observation, into the set of all the orbits that pass through these 3 base points. This variable is defined in the interval 0 to pi if the 3 base points are in the same orbit, in the same period. And in the interval 0 plus infinite if they are in different periods. So what we get with this function is a set of orbits that pass through these points. How do we select the orbit that we want? Well, we have different methods. The main one is to see the weighted root mean square error of the residuals of the position angle and the separation that we have it here. This is a typical result of one of them. But sometimes this is not a good method because for some binaries, mainly we have a very short arc of observations. The root mean square error of these residuals is very similar for all the orbits. So we can decide among them. So we have to use different parameters that the method gives us. So, for example, you have the Gaia parallax or the Hipparcos parallax or any parallax. We can calculate the sum of the masses, the systemic mass of the system, and see if we have a physically consistent result. Or if we have a main sequence system, a system formed by 2 main sequence stars, we can calculate the dynamical parallax. which is based on the mass luminosity relationship. So we can calculate the individual masses with this dynamical parallax and see if we can get consistent results. Or even if we have radial velocities, we can see the root mean square of the residuals or the calculated values of different control points that we can select. With respect to the orbit optimizations, what we do when we have a preliminary orbit is do a minimization of the weighted sum of the root mean square error of the position angle and the separation. But we have to be careful with this because this objective function is very nonlinear and it has many local minima. So we have the danger of getting stuck in a local minima and not get an optimal solution. So we have two methods implemented, a classical least square, which converts to the nearest local minimum, and it's a fast method. It converges in seconds. And then another method with this Rassing hopping, which we expect to get a global solution, not always the Gibbs one, but it's quite slow. It can take up to several hours to get to the solution. And for the results that we get, for Mira, we have these new orbital elements. You can see that the period is reduced to almost half of what we had, 276 years. And with this new solution, we get better results in the RMS, both for the position angle and the separation. And with the Hipparcos distance that we have, and with a distance based in the period luminosity relationship, we get these values for the systemic masses. 1.52 for the Hipparcos parallax or the Hipparcos distance, and 2.62 for the period luminosity distance. With this orbit, it's interesting that we have a periastron distance of about 20 astronomical units. So it is possible that we have some interactions between the binary components during the periastron. With the new orbit, the next periastron would be in 2076. So I don't think I will be working on this by that time. But the previous one was in 1800. So maybe it will be possible to find traces of this last periastron passage in the observations of Mira. Here we have the plot of the orbit. The solid line is the new orbit. The dashed line is the last orbit, the previous orbit. And you can see here, well, these crosses are the visual observations, all observations, and these dots are the new observations. You can see that it's a better adjustment to the new observations. And the residuals look much better. For Araquari, we have a new orbit of 39.5 or 4.6 years, more or less, with an eccentricity of 0.46. You can see that we get a better adjustment, and we have also made an adjustment of the spectroscopic element. So with this, we have also the Gaia distance, the Hipparcos distance, and I think in a limit will be presented a new distance of 260 parsecs in this meeting. The Gaia distance and the Hipparcos distance, they give unrealistic masses for the system, but this new distance, we get a better system mass. And because we have a spectroscopic orbit, and a spectroscopic solution, we can get, with the mass function, the individual masses of the systems. And we have, for the primary, 1.14 solar masses, and for the secondary, 0.55 solar masses, with a semi-major axis of 14 astronomical units and a periastron distance of 7. And as you can see, this is the adjustment, funding, and
We have questions.
You asked whether anything was known about Myra 250 years ago or so. But there is actually high-speed outflow from Myra that's been dated to about 1,000 years ago.
Mhm.
Which in your model would be 4 times the period. And indeed, the 1,000 years, if any accurate, could be the minimum distance.
Could be, but
With some uncertainties
With-
about
yeah.
what all of
yeah, we need to. We also have this image here. We made some rough numbers, and for the last periastron phases, the interaction of the outflow of matter should be at around 2 arc seconds, and you can see here, 2 arc seconds that we have this structure here. Maybe.
So this is an interesting approach. I have 2 questions I'm curious about. The first is there sort of, where you're sampling, I guess I'm interested in how the code scales. Is it better to have, more of these observations at different points in the orbits? Or, if you're taking a lot of observations close together in time, what's your ideal situation to
The
find a
best,
solution?
the best is to have a large arc of observations, even if we have less observations, because for short arcs, you have a lot of uncertainty. You have many orbits that can pass through those points and that have a similar residuals in the errors of the observation. So the best is to have a better coverage of the whole orbit.
And then is this code publicly available?
Is it?
Is it publicly available?
The code?
Yeah.
No. It's a bit dirty, still we're working on it. But our idea is to make it.
Thanks for your talk. I'm wondering about the orbital elements. We are usually used to use semi-major axis eccentricity, but it was curious to see that, for example, the orbital angles such as the argument of the pericenter and the ascent node of the ascending node, and those are very difficult to calculate by observation. So, for example, do these angles may change if you have more points in your observations, or they will keep fixed as the semi-major axis of eccentricity?
No, they can change. If you have new observations, they will usually change. But as you see here, for example, let's go back. For this orbit, for Araquari, that we have good coverage of the orbit, you will see that the difference between these orbital elements and the new orbital elements is not too large. So we have 110 in the inclination, around 90 in the angle of the node. So the less coverage of the orbit you have, the more it will change when you have new data points. So, but certainly, if you calculate a new orbit using new data points, you will get different values.
We thank the speaker again. Now we have Miguel Gomez Herrero. With the ALMA view of the symbiotic system Araquari.
Okay. Hi, everyone. Good morning. First, thanks to the organizer for this opportunity. And well, my name is Miguel Gomez from the National Astronomical Observatory in Madrid. And today we'll talk about our work studying the symbiotic system Araquari. And in particular, we will focus on the continuum and molecular emission from the innermost regions of the symbiotic stars, this symbiotic star. Well, as mentioned before in few previous talks, there seems to be a relation between symbiotic stars and the final structure shown by the planetary nebulae. For example, there are some processes such as jets, bipolar outflows, that can help to model, to shape
the axisymmetric stack structures seen, for example, in this planetary nebula. So let us start with a quick introduction to our favorite symbiotic star, Aquarius. This is the best studied type symbiotic star and consists of two stellar components, a Maria-type variable, it's an AB star, with a pulsation period of 388 days. The secondary is a white dwarf, a very hot and compact component. And it's also important for us to assume a distance for calculation for a model, and we assume 265 parsecs, very close to Timna, right? So, and it's also important for our comparison to know the Maira size and the orbital size, because we will compare the structure detected in our brightness distribution maps with this magnitude. So the Maira size is between 15 and 20 milliardsecond, and the orbital size is close to 100 milliardsecond. What you can see here is the optical image of our Aquarius, where you can see an axisymmetric nebula of 2 minutes in size, and also an equatorial structure here very close to the orbital plane, where both stars are orbiting around the center of mass. You can see here also in purple the X-ray emission, where you can see the jet emerging from the white dwarf. Okay, so this is a brief introduction. Now, what's happened with molecules? Here there is a problem because most of molecules are photodissociated by the ultraviolet emission from the white dwarf. So it's very hard to detect it. However, there are few detections of CO, one of the most abundant molecules, and also SAO and water masers. But if we want to study the distribution of molecular content in the symbiotic stars, we need maps. So you can see here, for example, a few examples of a very high angular resolution maps of the continuum emissions, of the SAO and water maser emission in this symbiotic star. And what you can see is the typical ring structure around the DDR stars. However, the SAO masers and water masers have a problem because they only take place under a very specific condition. As a result, even these maps are a very high angular resolution map, don't provide a general view of the distribution of molecules in symbiotic systems. So we need a thermal emission, for example, CO. A few years ago, there were a few low angular resolution map of Maira and Aquarius, but we aim to obtain a very high angular resolution. We want to study in detail the structure shown by the molecular content in Aquarius. We will focus on CO because it's a very important molecule, but we will also study other molecules less abundant, but it's also important to know a general perspective of the molecular gas. So we need high sensitivity and high angular resolution maps. For this purpose, ALMA is a very good instrument. So we are analyzing map of ALMA, the observations were performed between 2017 and 2023. In particular, we have observation performed with the extended configuration of the instrument in the band 6, 7, and 9 to have a very high angular resolution. We also have observations of the compact configuration of ALMA in the band 6 in order to study the most extended emission of our Aquarius. After observations, calibration, self-calibration, cleaning, imaging, we obtain finally maps with a very high angular resolution with, I don't know if you can see, okay, between 15 and 35 milliardsecond, and that means that we can resolve a structure with sizes smaller than the orbital size. So we can explore, for example, the intra-orbital structure. We have continuum maps, and in these three tables, what you can see is the detection of molecules. In total, we detect more than 50 molecules. For example, CO, SIO, SO, water, and one recombination line, H30 alpha. However, due to the low signal to noise ratio and some detection, we only have 30 maps. not too bad. Now, let's start with the results. I will start with the continuum. What you can see in the figure on the left is the low angular resolution map at 1.3 millimeter, where you can see and compact and intense emission in the center of the map that we identify with the emission of the AGP star and his close surrounding. And there is also here in this extension, this direction, there is an extended emission that we identify with the jet emerging from the white dwarf. If we compare the continuum maps of at 1.3 millimeter with observation of H alpha in the optical from Smith and College in 2017, we can identify the same structure in both maps. So, well, and if we observe with the high angular resolution, our query we obtain at 0.3 millimeter this map, and this one in the band 9 of ALMA. Again, we have in the center of the map a compact emission, and if we integrate the flags in this around this position, we can derive an spectral index close to 2, and this is compatible with the radiophotosphere of an AGB star. There is also emission, extended emission here and here in the band 6 and in the south in the band 9 that we identify with the closest regions where the jet is emerging from the white dwarf. This is probably the base of the jet in the radio continuum. Well, what's happened with lines? Here, there is the emission of 12CO. You can see the maps per velocity channel where you can where we represent the brightness distribution in different velocities. And as you can see, the emission is elongated along the rate ascension duration, and this means that probably most of material of 12CO is located in the orbital plane. Due to it's the most abundant molecule detected in our maps, so also the most extended structure with size of 1,300 in the right ascension direction and declination. Remember that the orbit is very close to the line of view, so probably this emission is coincident with the right ascension due to that. Bujarrabar and colleagues in 2021 modeled this important emission and they identify that probably most of components identified, for example, in many channels of velocity are forming spiral arcs in the orbital plane. Less abundant molecule, for example, CO, the sizes detected here are 300 and 100 in the right ascension and declination direction. Again, is elongated in the right ascension direction close to the orbital plane. There is also here an absorption at positive velocity that we will identify with material in falling back to the AGB star. And if we compare, for example, the central channel of the brightness distribution of several molecules, for example, CO and SiO, we can see how, for example, CO and SiO share different components, for example, this one or this one, and probably the SiO is also forming part of the spiral arcs in the orbital plane. Less abundant molecules, SO, water, show a more compact brightness distribution with sizes smaller than 100 milliardsecond, and that means that probably this less abundant molecule only can survive in the closest region to the AGB star where they has been formed. And outside of this region are photodissociated by the ultraviolet emission of the white dwarf. We model the emission, the compact emission in our channels, in the central channels, using a simple model to describe the emission and absorption. For the molecular emission, we use an expanding cell, and for the absorption and low excitation in falling component. So this is the resulting model. Due to the expanding cell is well characterized by the observation, the results are consistent. However, even we can reproduce the absorption at positive velocities. The information about this component is limited because we have not more information. So we provide a possible solution, for example, from material previously ejected by the AGB star, which is now falling back to the MIRA, or due to the pulsation layers of the circumstellar element. Okay, and if we have maps obtaining different epochs, we can compare it. So let me show you some example. In these two maps, you can see the brightness distribution of 29 SAO obtained in 2018 and 2023. And what you can see here is the predicted orbit for the binary system and the predicted position for the white dwarf in both epochs. And as you can see, in 2018, the emission of the 29 SAO is located in the southeast, and on the contrary, a few years later, the emission is located in the other side. This is probably due to photodissociation of the white dwarf or a gravitational pull. We are working on that. And similarly, in the continuum emission in the band 6, we have observations separated by only 2 days. And you can see here the distribution of the continuum. And you can see how the emission decreased by a factor 2 in only 2 days. This implies a very an important change in the energy of the system. Okay? This is tracing the jet here. And if we also use the H30 alpha and continuum, here in this figure, you can see in gray scale the H30 alpha emission, and in red contour is the continuum in the band 6. You can see how the jet is located with an offset respect the AGB star. This is tracing the position of the jet, and you can see how few years later the jet changed his position from this side to the opposite side here. So we can see how the change is varying in time. These are my conclusions. You can leave, so thank you very much.
Do we have any questions?
Very cool, Liam. Do you see any sign of this? Oh, so you showed the 29 SIO and suggest that there might be photodissociation going on along the orbit. Do you see this in any of the other molecules, in any of your other emission maps? Because there's plenty of lines that you detect that in this.
Yes, there are.
Probably also show this.
Yeah, there are more detection, and we can see how it change, for example, in SO, sorry. But for example, we have not explained still the jet, the CO. Thank you for your question.
You interpreted the radio continuum emission, not the radio, the millimeter continuum emissions speculated as arising from a radio photosphere. But would that be consistent with the very fast change that you're seeing in the continuum flux?
Yeah, I know. You mean this one, right?
Yeah.
Yeah. Yeah. That's a very good question. However, we think, that's okay, but we focus on only the central position, where we suppose that is dominating the AGB star with respect to the jet. But I agree, because maybe this can be there is some contamination from the jet. So I mean, this is an estimation. So okay, it's compatible with an AGB star. Now we are obtaining the spectral index of the most of these observations, and we obtain a value close to 1. So okay, there is some contamination, but it's not so strong. Thank you.
Do we have another question?
Can you go back to the X-ray plot that you showed at the beginning?
Sorry?
The X-ray, it was like maybe the first or second slide you had an image.
This one,
Yeah,
right?
this one right here. So here's another S shape. So is that jet precession? So there's another S shape in this jet, right?
Yes, this is the jet.
So is that jet perception? Is that what we're seeing?
Yeah.
Okay.
Yeah, it is detected in negative And I guess Tina will be talking about those features in the jet. Do we have more question? One more question? If not, we thank. And now we have Tina, the next on developments of the R query outflow during the recent Veriascom package.
Hello from me as well. So you have probably now realized that R query in the symbiotic field is like the butterfly nebula in the BN field. It's the benchmark, everyone talks about it. It's one of the best studied symbiotic binary, and yet we have many questions still. Everything that was questioned yesterday being as problematic in the planetary nebula field, like single episodic periodic outflows, knots, complex hydrodynamic interaction, 3D structure, to say it a few, it's all present in this single system. And outflows, it has many. The most known, and about 100 years we have known, is this hourglass nebula here, together with that precessive large-scale jet. And there is a model of it done. So now we are in the hot gas regime, because the previous talks were more in the molecular bands, but now we see the hot gas. These are all optical images. And yesterday, it was mentioned that when you go deeper and larger field of view, you find surprising things. So this is amateur image from 2016, where Mike Sidonio, he exposed 8 hours. So this is the VLT image, professional telescope times. It's a couple 10 minutes exposure time. Here he exposed 8 hours, just because he had the time, even though it's a much smaller telescope. And what he discovered was a very large faint arc in oxygen 3, which has not been seen before. So that's the largest outflow that we nowadays associate with R aquarium. And when we go to the other extreme, zoom into the center, we can see with the sphere a very detailed inner region. This is the base of the jet. You can see that the morphology here is very complex. It's not uniform. It is changing in a matter of the brightnesses of these features are changing in a matter of months. In the outer jet, we see the changes also morphological, not only brightness, in a couple of years. And we have monitored this target for decades, and we still don't know exactly what is going on. And first, distance was mentioned. So distance to R Aquarii has been under debate. Their values range from 180 to 390 parsecs. Gaia distance is not reliable. This is the highest end. It's not reliable for R Aquarii because it's a wide binary system, and you can detect not only the binary motion, but also the blobs around it that we discussed once with Jaroslav. So we have favored, and our team has favored the expansion parallax of the nebula. I know it was mentioned yesterday that it is not reliable, but I will confirm that in this case it can be. So previously we considered the distance 180 parsecs. Oh, I think I'm outside from the YouTube people. But with the updated expansion velocity from these models that you saw before, we have now updated also our expansion parallax, and we find that the distance that best fits with all the other possible ways of determining the distance is 260 parsecs. It fits also very well with the masses in the binary, for the Myra variable to be 1 solar mass and the white dwarf to be 0.75 solar mass. So the distance is important because I am showing you the analysis, the expansions in the plane of the sky. So in order to put that into physical sizes or to find any H's, we need to define the distance. So this is what we will use. So starting with the furthest or the largest outflows of Araquari. So while this is where we started from, there was another amateur astronomer, Peter Goodhue, who a few years afterwards exposed more than 33 hours. So what we saw then was that it's not just a faint arc, but it's a thick elliptical structure in the north, and in the southern part it is more diffuse, asymmetric. And first time when I saw this, I was so sure that it's like a classical case of being a result of a central star moving in the plane of the sky. So if you would imagine that if that star would move in that direction, then you sort of drag behind the nebula and it gets disrupted like this in a couple of tens or thousands of years. However, Araquari is moving in this direction. So that doesn't explain it. So this is the image, but obviously we wanted to know more. So we went for the spectra that Martin kindly obtained with the ALFOS at the Nordic Optical Telescope. This is a professional telescope. We cannot expose hours and hours, so we have 1 hour exposure time, and we placed the slit in a way, this is the length of the ALFOS slit, the maximum length. We placed it in a way that we get the most of this faint structure in the brightest area of it. And we also placed 2 stars on the slit, because otherwise it would be very difficult to reproduce the slit in the plane of the sky, that where we actually have placed our slit. And this is our, get out from the field of view again. This is the 2-dimensional spectrum, which we, after the reduction. So you can see here the vertical lines as our reference stars. We can clearly detect oxygen-3 doublet and nitrogen-2 doublet. Also, we can see oxygen-2 down here. However, its flux is a little bit questionable because it lies in the blue end where ALFOS is very noisy. And as you can see, it's quite faint. The spectra is faint, and these are the only lines that we see. So what we did was that we combined along the slit, defined 2 areas, A and B, and the A was here where the oxygen-3 was the brightest, and the B was here where the nitrogen-2 was the brightest. So then we got combined surface brightness profiles, and we hoped to gain more signal to noise, to see more lines, but we didn't. The only thing what we saw a little bit more, or what we were able to detect, is the little H alpha there between the nitrogen-2 lines. So unfortunately, we don't have enough diagnostic lines to say anything else about this large structure around Araquari. The only thing what we can say, because in the position B, the nitrogen-2 and the oxygen-3 have a similar flux levels, so probably it's a low excitation nebula, but if it is a planetary nebula type or maybe from a nova type eruption, we cannot really distinguish between those. What we can do, however, with some assumptions, and also even though the spectra was very low resolution, but we could get the range of the velocities that it has, and they are typical for planetary nebula type, about, let's say, 20 to 30 kilometers per second, and taking into account the distance and the extent in the plane of the sky, which in this direction is 6, almost 7 arc minutes, we can get the age of 10,000 years. So this is compatible with the planetary nebula ages. And because there is an obvious positioning in the plane of the sky very close to the Araquari, so, and it has a similar tilt angle as the orbital solution of the binaries, as well as the hourglass nebula here in the center. So it is clearly an outflow from the Araquari, from a previous evolution of the white dwarf, most probably. Moving into this central area, but still relatively large scale, and now concentrating on this large scale jet. So as was mentioned already before, Araquaria recently went through a periastrum passage, and while the periastrum passage itself, where the white dwarf goes gets closest to the Myra variable, but also it happens to be the inferior conjunction that that Javier pointed me out some time ago. That means that the white dwarf goes. So you look in this direction. The white dwarf goes between us and the Myra, and while this does not last for many years, it's only maybe 2 years, considering that the white dwarf also has a accretion disk around it and so on. But in the light curve, we see influence of this periastrum passage, which lasts about 6 to 8 years. And while the light curve is usually like Myra pulsations with the orbit of 1 year, with the period of 1 year, then during the periastrum passage, these orbits, the amplitude gets smaller, so something is suppressing the visibility of the pulsations, and it lasts for several years. And our interest, and as we are monitoring this jet for many years already, so we noticed that by the 2019, when the periastrum passage in the light curve had already started, we saw a very big change here. These images are 45 to 90 arc seconds size, and we see that this part of the jet, this is northeast part, has completely disappeared, like someone switched off the torch to see it. And this did not happen instantly when the periastrum passage started, but the HST data in the times, in the periods between, showed that it gradually faded away. So we were waiting many years to see if it will recover. And only now, from August this year, we can see that finally, while all these years, the emission was not detected here and the exposure times are roughly the same, so we can compare these images with each other. Suddenly here, the periastrum passage in the light curve at least ended in here. And finally, we have emission back in there. So something has blocked either the illumination or the ionization source that is making this jet visible. It's not recombination, because the other emission lines, we have images and many emission and several optical emission lines, they show similar changes in the similar timescales, because if these are all oxygen 3 images, if it would be recombination, then the changes in oxygen 3 would be much faster, but they are not. But to distinguish between the other phenomena that are happening in this system is very complicated to disentangle. And I am not the theoretician, so I am the observer part. So, but for modelers, it's very complicated to model all these processes, photoionization, illumination, scattering, and also the matter is moving outwards at the same time, how to take it all into account. Now, talking about now moving into the very center. So this is the orbital solution as we see it in the plane of the sky. The image that was shown before was in a different orientation. But here we see the Myra. This is the size to the scale, scale to the size, no, size to the scale. And this is how the white dwarf goes around its orbit. So as it was, it's the first time that we were able to monitor the periastrum passage in this system with the modern telescope, with the modern telescopes. And that's why we also wanted to give input for refining the orbital solution. So we applied for a very high resolution speckle imaging in order to separate the binary the companions of the binary. And now, as I'm running out of time, I will not have time to go into very big details, but this is our final example image. These are already known features and some of them were shown before, but what we found, indeed, we found a second very faint component. It was too far away. If you remember the previous image, we were expecting something in 10 milliarc seconds. We found it 3 times further away, and it was moving in a broad direction. It was going downwards, while we are expecting it going to the east, where the white dwarf was supposed to go around the orbit. So we were unhappy, but then when we plotted it to this image, and I'm out of time, but I will steal that minute because the discussion is after me. So we saw that it's actually moving outwards, and that it must be ejected matter from the central binary. And this has been like a long debate whether the jet of Araquari is activated during the periastron passage or not. And in the optical range, it has not been shown that it actually is. So here you go. When we go back in time with the expansion, with the velocity that it expands, it goes exactly to the 2020, which is the periastron passage. And there is no time for this. But we also noticed that there is actually a two-sided jet where this not very faint knot that we discovered is inside. So here are my conclusions, but I will steal another minute because I think it's very important to emphasize that this type of observations to get the evolution of the extended outflows in the plane of the sky, it takes a lot of effort of many people and many years. And you are not the only one having a birthday today. Romano has a birthday today as well. So it was already 40 years ago that Hugo Schwarz, who tragically died, or I think already 20 years ago or so, who started the survey or the hunt of the symbiotic nebulae, and some of them are also planetary nebulae. Then Romano became his PhD student in the beginning of 90s, while I was still like this. I was already born. I had no idea of the stars. I was afraid of darkness. So I was not in that business yet. And then some 20 years later, I became a student of Romano. Now Romano is active in other spheres of astronomy. So I am left here, and it's also an effort of many other people. Denise has worked with Araquari. Miguel has done a lot of work in this. So it's effort of many people, and it takes a long time, but there is no other way. Thank you.
Thank you very much. So we have questions for Tina? I do have a comment. It is so it seems that the jet disappears in the optical during periastron passage, and the X-ray emission is the maximum.
At the periastron. Okay.
Yes.
Well, but this
It's
is
actually just a few years after periastron
okay.
that the X-ray is maximum when you see the disappearance of the jet.
Good question. So just, I don't know the system too well, but so the periastral passage and energizes accretion, there's extra accretion, right? And it's still wind accretion, even at periastron? Yes, there's no rush over flow.
Yes.
Yeah,
So
it's not close.
Is there a change, can there be a change in the orbit due to that interaction, whether it's drag or tidal or whatever?
I think that's more of a question of these who model the orbit.
Yes.
I don't know.
It has to be very compact in order for the tides or the drag force to be actively changing the orbit, and this is very extended.
Probably it's not the case, but probably in a similar object. If this white dwarf explodes as supernova type 1a, the remnant will become like a planetary nebulae, like non-soccer showed up before. So you will have supernova remnant with jets and so on. So it's question.
We are still far away from this because the white dwarf mass is about 0.7 solar mass, and I'm not sure if it's actually.
No, we are talking about in general the picture, no, that you have the nebula around the planetary nebula. So the supernova remnant will show up like a planetary nebula with jets and so on.
Mm-hmm.
One last quick question.
Hello, I'm just impressed because I wonder that there was a timeline from 2002 to now, and instrument quality has been changed from 2002 to now. And how can you be sure that these phases are confirmed?
I don't think I understood that. What is confirmed?
I think those lines might be unseen or
due to the quality of NO and OT or reality telescopes?
So these are mostly, it's the same telescope instrument
Yeah.
and the filter is wide enough to capture everything.
I see.
And in some cases, we also have repeating observations which show the same pattern. So we are pretty sure that this is real.
Thank you.
Thank you, Tina. Now we think of the future. Can I have a question? So it's been a very busy morning. And we thank again all the speakers. I've been monitoring the slide and there's some couple of questions on common envelope. I don't know if you saw them. I think EJ posted a very controversial comment saying that all protoplanetary nebulae are descendants of common envelope evolution. You did? Okay, sorry.
Guillermo doesn't have Slack because it's
Yeah,
computer
you
school.
said that.
So this is just a, just to get some discussion, but I also have something about this sort of symbiotic essays. But so can I start from the other one? Because the talks have just happened and.
Yeah.
So these S's, which I assume is for symbiotics. So these are processing jets. Yes, and there was an earlier talk that had an O2 image where you can only see the S, right? So they're very distinct features, they're not illuminations or anything. So, and they make bubbles, right? They make bipolar structures, they inflate, Noam has worked a lot on jets, inflation of bubbles. So there's two types of bipolar structures, also true probably in PN. One is the ones that are to do with, the butterflies are constrained, and also your object had that as well as the bubbles. So this is important because we look at the morphologies to infer what happened, and we often say, oh, bipolars come from X, but there's more than one type of bipolarity, and so do we in planetary nebulae see the S's? We do, or on protoplanetary nebulas, and do we confuse them with the other types of bipolars, which are more the butterflies coming from the constraining? And do we just make a very big confusion as to what causes? Oh, bipolars are always due to this phenomenon, but there's just so many more bipolarities. So, and I
Just a big comment.
Yeah, and then I'll relate to.
So I forgot to mention also because I was out of time, but in the Araquari, this hourglass nebula, the big one.
The big one.
Yeah, this we have come to the conclusion that this is like from a nova type explosion about 450 years ago, while the jet is still active, and the outer features of this S shape are about a few hundred years old, while the inner part is still being active. So these are two different outflows. Yes, well, they are both probably from the white hole.
I disagree with that idea.
So I was just gonna say, so I think precession requires a pretty particular set of circumstances. And so like you need the jet expansion velocity to be comparable to the orbital velocity. So otherwise the orbit was going too fast, it was like continuous outflow. But I had an HST theory award some number of years ago, maybe a decade ago now, where I did look at this in PN, and I think the percentage of them that have S shapes is pretty low. It's like a few percent. And I think it might have been up to like the PBN sample was maybe at most 5%. So I don't think you see it a lot in those systems.
Yeah.
But I've seen two so far at this conference, so that's a lot to me.
I disagree. There are some cases, like I see for 593, you have outflows going one direction and orthogonal to it. So in general, precession is small angle, but some cases it just ejecting things at almost crazy directions. And the other thing is that yes, there are different kind of bipolar planetary nebulae. You have those butterflies with narrow waves. maybe even dusty lanes there. And then there are also those with large ring-like structure, and those are different. Those are different in H2, those are different in other parameters.
I disagree with the NOVA here because the X-ray emission from NOVA explosions, you stop detecting it very fast within 50 years. And in this case, what I think is happening is that the jet started and then stopped. So it created this large hot bubbles, and then the jet activity started again, and then we have a new bipolar internal nebula inside this hot bubble that I don't think it's a NOVA explosion.
And in Joel, in some PN with the H2 structures, which we're looking at right now, there seems to sometimes to be S-shaped when you look in radio, which is rare and it's faint and cracked images, but you get a 3D picture for free.
Well, it's on
Right.
the,
There's an S, and sometimes looks like illumination. So there's an S in that one. What is the name of that one? Is
this is NGC 6302. Well, okay. Yeah, so NGC 6302 obviously shows what you might call an S. Or is it just the heated interior of an hourglass? I'm not going to answer that question. However, I will show another one tomorrow, and then or Thursday morning that is, and then examples of nested outflow structures, which Martine was just referring to, I think, where the dynamical ages become very important. It becomes really important to understand what the dynamical ages, I think, of these different structures are, and to try to understand if we're seeing the results of an individual event that is plowing into different densities. And so we're seeing different distinct outflows, episodic, or we're seeing one event that was pretty sudden. I don't think we have answers to those questions yet. And there might be, and of course, as I said yesterday, I think the answer is probably yes.
While I slowly walk towards you, I will say that the advantage of symbiotic systems is we are seeing the accretion and the ejection in human timescales compared to planetary.
Thank you. Just to continue from what Ursula said, if you have jets driving into a more or less homogeneous medium, like we see in some extragalactic nuclear jets in galaxies, you get a diamond-shaped nebula on the outside. If you have a spherical wind interacting on a constraining disk, you get a typical figure 8. One thing about 6308, for instance, if the disk is warped, then you get an S-shaped on the outside, which in fact you do see in a large nebula. Whether or not a jet is sort of a secondary thing after that, I don't think anybody knows.
I think this is super important. So, okay, we established there's nested structures. We've seen it in the symbiotics, but we've seen it in PN as well. And I think the picture in the program is a good one. But the question here, what is the S from? Not necessarily from processing jets. Because otherwise, if they're all from processing jets, what you're saying, there's an event that creates some ejection, which is bipolar in nature, and then there's something else happening later on that creates maybe an inflated bubble with this S. But you're cautioning, watch out. Yes, doesn't always, it's not a unique outcome.
Let's see the S. Yeah.
That's not a good picture.
It is of interest to see bits of this go together, and developments already 6302. And if you look at the comparison to that to Aquarius, it's quite amazing. Bruce Bellick has been pointing it out to us. The structures look very similar. And now that we found the central star in 6302, it's even more symbiotic-like. A very red star, which is also 220,000 Kelvin. There must be more than one object there. And so the similarities become more and more obvious. And so precessing jets, I would say M29. You can actually see the precession there in action.
Just
When talking about this bipolar outflows, when I see this S shape, it reminds me of some radio galaxies because I remember looking at some radio galaxies like Centaurus A, which has this shape. And I wonder, for example, if there is a connection between the extension of these outflows and the shape, because I remember that these people that study radio galaxies said that the extension of these jets are due to the accretion efficiency of the black hole, but I don't know if it's the same here.
But I think people are being much too cavalier about comparing small things like this to accretion around a black hole. If you have a 10 million solar mass black hole with a relativistic disk around it, the precession of the disk is lens theory precession. It is drastically different from this kind of stuff, which is not, in our case, you have precession that is tidally caused. But the disk around the 10 million solar mass black hole will do something drastically different, I guarantee you.
Now hold on to your chair, so as a report. No, you want?
Well, 20 years ago, I did a series of papers comparing the shape of AGN-shaped nebulae. I mean, this cluster of galaxies, which are huge. Vincent, they are huge. I compare them to planetary nebulae, okay? So you can go to a paper by me, Soker, and Bisker was an undergraduate student, and it was 2006. Don't go to the journal, go to the archive, because there we put the pictures. And you have pictures comparing AGN in a cluster. The largest one there is 1 million light year. Compare with the planetary to see the same structure. They put it in tens of meetings. I can put it again. I will put it on Slack, okay? So you see, actually, you're like the same structure, same mechanism, precession in jets, and you have multiple jets, and you could form clamps. The whole mechanism, the whole jets, the jets are everywhere. I mean, you can have other mechanisms that work for one particular object, unlikely, you know, also. So, yes, they're the same.
I remember Carmen had a question or a comment before.
Yeah, well, I was gonna ask a question to Jaroslav, but then I thought I have the answer itself, but still, there are not so many plasmids for a pure symbiotic system. I was going to ask, what is the fraction of this, genuine symbiotics that have envelopes like this in the optical or in other tracers? And then I know that CO emission, for example, from these guys is much weaker than for normal AGV stars in general, or even than for PPNs. So it is very hard to find these nebulosities around. So, I mean, does that mean that when you see when there are, for you, PNs are imposed, or it might be difficult to differentiate between PNs and symbiotics. So the presence of these extended nebulosities, do you think this could be maybe a difference or a key point to distinguish? But of course, PNs, PPNs, some of them may also have actually a genuine symbiotic system here, not an AGV star and no?
No, Bruce knows, he's looked all the slide, but there's nothing, there's no binaries in PPM. Except very line.
Our binaries in pieces.
Well, except for the Bumpinko type objects, the PPNs.
No, there are binaries.
No, there are. Okay, but then they're supposed to be binary.
No, for PPNs, there are many indications.
Okay, well, this is an important point. Well, let's just wrap it up and then let me. So did you, wait, Carmen, you had that was corollary. Do you had another question for the symbiotic?
Well, no.
What did you want to, okay, that's okay. I just thought I'd, sorry.
It's true that we have not found binary systems in general at the centers of center star of P-band network. But there's one very well known P-band network, I005, for which a binary has been found directly by the velocity equation.
Okay, so, but And it's supposed to be
Yes.
with a hundreds, oh, that's right, yeah. So actually, so this is a very good point to be made, right? So of course, there are binaries in PPN. If you look at the red rectangle, that's the case. But I would. Okay, you know how you read a lot of papers over the years and then you form these mental pictures. And my mental picture is got a class of PPN, which is the ones Bruce has looked at for a long time, looking for the binary that must have done the collimation. These are the really collimated objects. Ravendra has published 1 million papers on that, right? When you look at those, they have a post-AGB in the middle. And when you look for binarity, because you expect it to be there, you usually don't find it. You have a lot of pulsation and occasionally something on 30-year periods, a couple of times. You have maybe 2 or 3 objects. Then there's the Hanses objects, which are post-AGBs. The star is identical in the 4,000 to 7,000 or so Kelvin. And those are all found to have this infrared excess, and then they have this, and then they're all binaries, and tend not to have a velocity, except a few times, like the red rectangle is a good example. So I make this into 2 categories: the post-AGB binaries, no PPN except sometimes, and the PPN never or mostly without a companion. So there's that Javier another.
Without an observed companion.
Observed companion, yes, okay, yes.
Well, few just point for people. I want to point out a few things. The red rectangle and the others, like the red rectangle, many of them have levels of large levels of not so prominent, but they do have. The difference is that the mass.
Slow.
Yeah. So it's really different having 1 solar mass ejected or having 100 solar mass ejected. That makes it different. And I don't ask me why, but the ones that have detected rotating disk and a detected binary positively detected are the ones that have low mass. Don't ask me why. But then there is the case of OH231, where Carmen has detected a rotating disk. So it's not a binary thing yet, but it's a rotating disk. Then we have 1 case. Well, we need to find more cases. The problem is, as you, Carmen, probably know, what she knows very well, is that when you have a huge amount of CO outside, looking for a rotating something very, very deep in requires ALMA time probably 7 to 6. And they are not granting time for that, for whatever reason. I mean, and then in the red rectangles stuff, you can readily detect the rotating disk because there is no so much gas around. And when you even when you look at the CO1 to CO2 to 1, you can spot the rotation disk right away because it's the most prominent thing, or almost the most, it's not so faint comparison with the other stuff. But it's true, in the very massive ones, there are still no detected binaries. But
Except for this 1 case.
we have not.
And also for M2-9, there's answers.
What is massive or massive? What?
Okay, hold on a sec, one thing I'm gonna tell you, Carmen, and then we have a question.
And somebody like. There. You
Go
go.
ahead.
You go.
Yes, it is a problem to empirically and directly detect binaries in what we probably or you call classical PPNs, which are the ones that have a lot massive, prominent, and the reason is what Javier said, there is so much stuff. I think it's very difficult to get in, even to find rotation disks. But so that's the main reason. There are only a few confirmed binaries.
Well, in the radial velocity, you can, like, we know some do not have a binary where, you know, in certain positions.
But those you can only do towards objects where you see a bright central star, right? I mean, most of PPNs have very thick dusty regions in the equator. You cannot just do this radial thing. So Bruce is working probably with a subsample of PPNs where you can see the central star.
Yes.
Okay. For the others, we don't know. From the fact that they are bipolar, multipolar, etc., we believe there are binaries, but we don't know. But I wanted to mention that M2-9, for example, we observed the jet that is just now being launched from the central system.
by the way, it's not S-shaped, it's mirror
It's
symmetry.
on
It's mirror symmetry, it's made like that.
It's just-
Okay, and the jet is rotating. Okay, so that is an indirect sign that it is launched from a rotating disk, and that is plus, well, for this object is actually one of the ones that was classified also as a symbiotic.
Thank you. I would like to start with the start of Jaroslav talk, because in the beginning his motivation was that there are many simulations estimating the number of binary or the number of symbiotics, and it's way lower than the value he's found even now, I think, after his conclusion. It's so the parent population of all those different systems is what we need to study, because we are not sure that they are really coming from the same population in the first place. And so to see, because there's a lack of symbiotic systems, which is significant, and there is a lack of, I mean, we are not sure whether we talk about the same parent population of objects.
That clarifies, so the post-AGV binaries could be given rise to symbiotics when the G-star companion becomes giant and the other one becomes a proper white dwarf. But the numbers don't match. I mean, the time scales, I don't know. We don't know, this is hard to tell time scales.
And I just wanted to reemphasize a point I made earlier in the talk, which is that so you can have a close binary interaction where the companion is destroyed and you get almost another factor of 10 out in energy. So we just have to be a little bit careful, because you should expect at least some of these systems to have been destroyed. You wouldn't find binaries, but you would have had binary interactions.
So then here I can inject my sentence. So it's good to make just simple statements which are almost certainly wrong, just to be clear. So all PPN with no found companion or have merged. And the reason to say this is that many of these PPN have very high linear momentum. And if you look at the thing, well, there's a what is the Blackman and Lucchini 2014, they show that a whole bunch of this high linear momentum PPN must come from the type of accretion that you could get only in a common envelope. However, it can't have been a normal common envelope with a surviving binary, or you'd have to have a closed binary, probably would be a central star of a PN. It would go straight to the hot regime by being shaped. These stars are still post-AGBs, are still large, so they didn't do that. So hence, and we don't find the companion, so hence the merger nature. So is this a valid hypothesis that to be disproven, as we do in science?
I think it has validity, because the same, like Javier mentioned earlier, that there's this dichotomy between the masses in proto-PN, where you have the massive proto-PN and then a very low mass. It's the same dichotomy in the linear momenta. So the most massive ones are also the ones that have this extreme linear momenta, and then the lower mass ones, the ones that have disks, they don't have this linear momenta. So not all proto-PNs, but maybe 80%, which is the fraction that are very massive and very high.
So that's a really good number, right? Because in the end, the momentum doesn't lie, right? So the engine can't have been.
Well, just an announcement. In December 2026, we will have Gaia DR4 that will have variability for all the stars. So with that, we can do some, because I don't understand that. So everybody will stop it. I don't think this is really.
Oh, no, more data.
And I'll talk in some more detail tomorrow about observations of PPN and looking for binaries and what we found, and maybe another one. Hopefully.
That's the one you were talking about.
No, he mentioned the same.
Okay, and part of the
Well, finally, I have a microphone. First of all, I start from the end. I'm not sure if DR4 will help with many of these because, for example, for RVs, yes, there will be epoch data, but many of these objects are super faint. So, like, there is no hope that these RVs will be actually useful for those. If you have a magnitude, I don't know, 9 star, yes. If you have magnitude 15 or 18, no. So I'm not sure if DR4 will that help. And now I can get back to symbiotics. So first of all, with the nebulae, there is just very few with the resolved nebulae. All of them have nebulae because we see the nebular continuum, we see emission lines. There's
20% have.
the resolved nebulae.
Yes.
In optical.
Yes, with the current knowledge. But we will try harder in the next years.
But yeah, but the one of the problems is that our query is 260 parsecs. It will put that star not to 5 kiloparsecs, which is super small. So that is the main problem you will have, but you will not resolve that just because it's small.
That's the case for at least 20%, because they are very distant objects.
Yes, but they have not been really studied properly either. So we will try. And the key is to go fainter. You know, they are further away, so they get smaller, but then they might have some fainter, larger structures, but that takes a lot of time.
And if I can react on the numbers, one of the things, what I think we have a problem with the predictions is that in many cases we are overestimating the symbiotic lifetime. So that leads to these numbers of 400,000, which it doesn't seem that the symbiotic interaction lasts that long. And the second thing is that in any population study, you need to get to the symbiotic phase, which therefore, for example, I don't like when in the same group there are red giant main sequence are interacting included, because it's super simple to get to that, right, from the binary point of view. But to get to the symbiotic stage on this period with those eccentricities we observe, you need to do something in your the binary life to get there. There is a common envelope that you avoid or survive or so on. And the common envelope is one thing which I think we don't understand well enough to do population synthesis for symbiotics. And the second thing is the mass transfer, how it works. And okay, this is now happening. Let's hope that will bring some new results. But you know, all this distinguishing between the Roche-Loeb filling giant, just for example, based on ellipsoidal variability, which we observed, it doesn't work. I did the interferometric studies this year, 2 papers published, and even those that shows ellipsoidal variability are not filling the Roche. So we are far from understanding how the mass is transferred, but you need that.
Yes.
To estimate the amount of symbiotic stars. So we are far from that.
I know it is tempting, but I think, well, at least I like to not to simplify things too much, like because nature is complex, and if this is shaping results maybe from the interaction between one big star that is losing mass, the other one that is catching some mass and launching jets. There could be so many configurations.
Yes.
So it's not reasonable to expect that only one channel is going to work and produce everything. I think there are many processes involved. And also we have even observed a change in the way the binaries are interacting in the same object. Like OH-31.8, for example, the large-scale nebula was ejected in a different way because it has very different properties to the bipolar ring that is being ejected now.
Yeah.
The one that is ejected now is just slow velocity, very symmetric. It doesn't have momentum excess, whereas the other one has much larger velocities. It is asymmetric. It has a huge momentum excess. So even in one object, we are seeing that, you know, the interaction mode was not the same. So
yeah, indeed, we must find patterns rather than
yes.
So
yeah, and there are objects with, as I think Jason said, or Martin said, orthogonal bipolar ejections. It's
probably more complex than we would like to be.
For example, if we now take the new calculation for the NERA system, so eccentric, it means that every time it goes to the reactor capacity, it goes into the wind rush flow overflow, and then that will change or the actual orbit of the system. It will go from wind rush flow overflow to the wind accretion regime. So this system within now will be very dramatically will be changing the cylindrical parameters. So this is very dramatic with the new orbital properties.
Yeah, about Myra with the old periods, 500 years, we were expecting only this spiral perturbation on the normal AGV that was we're expecting, apart from photo dissociation very close by. But now, if periastron gets much closer, then we can try, as we did, to search for past periastron, and of course somebody will just do it for the next periastron, but maybe it becomes much more active.
Yeah, it has to be changing this accretion regime and the mass accretion efficiency within the orbit.
And that changed only because of the new observation, because the old ones suggested that
Yeah,
it
it was
was period orbit, and now it's totally changed.
Yeah.
It also depends on whether the accretion is able to be maintained during the wind accretion phase. Because of it, 90% of the orbit, it has a Roche overflow, and only 10% of the orbit is wind accretion or liquid accretion. Maybe it's able to maintain the disk, and it's less dramatic. But is the accretion is destroyed and is in some way periodic accretion, it will be more dramatic change.
Yeah, but accretion can take place even though you don't have an accretion disk.
Yeah, sure, but the regime, the change of the regime could be more dramatic or less.
I don't think so.
So if I can just say one, so there's kind of two things we looked at. If you get a merger to have a jet, it's going to be very, very fast and dramatic. You're going to have distraction of something, a ring around the core and some really impulsive ejection, which by the way, many ppm, we do see evidence that it's been impulsive, we can time it exactly. If it is something that's going around more gently, then you can have all kinds of jets, but they're different kind of nature. I want to ask a question. Who in this audience has read or even heard of two papers? Well, it's not really two, it's a class of papers. Anyway, Ondracek.
No, common envelope.
You've seen that, okay? And Veta papers. Mark was right there. So these people in this is Heidelberg theory group doing a lot of common envelope and related work. They're starting to really get to the bottom. Well, they're starting to get to the bottom of this type of violent common envelope that gets to really big disrupted ejecta with cones and all kinds of things. That's really the beginning, but pay attention, right? Anything that's coming out of the Heidelberg group is going to be great. And Marco particularly, do you want?
But this are not the jet we are looking.
No,
but it's not the starting, the second stage. The first one was 30 years ago when I proposed a distorted envelope, okay, 92. It was an analytical one, yes. So the model you talk about is that the envelope is distorted, and because of the distorted along the funnel, yes, you have 1 foot, 2.
But with magnetic fields as well. So it's starting to be more complex.
You have magnetic field. So very happy with the magnetic field. But what does the mechanism is that you have the envelope is very distorted and you get two outflow. Okay, so two things. First of all, this idea I put forward in 92. I can find the paper, it will take me 15 minutes. Those were, you have 2 million papers in 90. Second, these jets they are like, it reminds me of the jet of Pulsar. They go up and then they bend. They are not, and they are not the jets we are looking for with high momentum and so on. These are very nice simulations, okay? And I think it's correct that they are distorted, and these simulations are correct. I believe in the results, but I don't think these are the jets we are looking for. So we should be very, very careful what we call jet.
Totally agree. But Marco was working on from those papers, and he's also you're looking also more massive of systems as well. They're starting to look at the winding of the magnetic field, which is exactly what Eric Blackman and Jason proposed ages ago. So that's where you want to comment, Michael?
Oh.
No.
Yeah.
Yeah. So sorry, that's good, actually, we're preparing the field. Any more? Well,
This is just on the top of my mind. I'll just say it briefly that there is an obvious way to distinguish between planetary nebulae and symbiotics. You know, if you're talking about this object, for example, it has a 200,000, 250,000, someone said 400,000 degree central star according to the excitation of the nebula. So you know, this is almost undoubtedly the mass loss you see here is undoubtedly coming from this object.
But we do have hot stars in symbiotic.
What's that?
We do have hot stars in symbiotic stars, as
Yes.
much as 100,000.
And more. Okay,
And
so
more, yeah.
so then I withdraw my comment and I'm so this is what bothers me about this object and many of its ilk is that the dynamical timescales involved are thousands of years. So
That is
why would this thing be still at, we've talked about this other planetary nebula meetings, right? Why would it still be at 250,000 degrees? Accretion, blah, blah, blah. So I guess I'll stop there. Not really more.
Thanks. Now that we have seen that in a single orbit, equine accretion regimes may change. So once the Roche-Loeb overflow is reached, is it possible to go out of that, or it's now as it begins, the common envelope is inevitable? Is that
A really key question. The answer is that there must be so once you go into Roche-Loeb overflow, it's incredibly easy to fall into the common envelope, right? That must be true. However, there must be ways to save the system somehow. And Noam has talked about grazing envelope evolution, where you accrete and blow jet and you don't fall in. But that is a really big question. We don't know. There's a lot of work right now on stability of mass transfer at Roche-Loeb overflow. If the mass of the companion is higher, you stabilize the system. But when you have an HUB donor, which expands when it loses mass, it really pushes into L1. So it's really hard. And I think that is the crux of also Hans's object, which uses mass transfer, which is very hard because. So
that all global even.
But that's
finally we get got into the end group in it was a long time, so 1847, 1846, 1837 to 1850 something. So Eta Carina, I think, got really into the envelope of Roche-Loeb overflow, and it's still there.
And plus, Eta Carina has a period of about 5 years, right?
Yes.
And we don't really know the radius because it's a mess in there, right? But the periastron, and it's got an eccentricity of 0.9, super high. It goes really close to a very large mass losing star. So the interaction must happen there. So of course, but then these are massive stars. They behave very differently from HUB stars, right? They don't expand. So again, it's not very easy to extract
grazing
it.
envelope evolution. Look for grazing envelope evolution. So, my view.
Next issue.
Okay, can I ask a very stupid question?
Yes.
What distinguishes a common envelope from a luminous red nova? So when does it become an integer and when is it in common envelope?
Right, so the luminous renova may well be common envelopes. Whether they merge, we don't know, because we've not seen what's inside yet.
So how can I separate them?
We can't.
Not
yet. In 10 years, 20 years, when it disperses, we might see them.
I prepared slide on this, if I have so many.
I wanted to go back again to the specific case of our artillery, because like studies, I mean, the objects that I normally study are not so well characterized. I'm always speculating about, the properties of the binary system because I cannot see through the nebula. But in this case, I mean, the orbit is super well characterized, the central star, we know the masses, and I think we even know the mass loss rate of the ongoing mass loss rate. So, I mean, with all this information, I mean, what is this for this object? And maybe not trying to go to the super details of why the outflows look like this there, but what is the mode of interaction that is most likely in this object? And also, the jet launching, I mean, if there are different models, I mean, this question, I guess, is for the models. I mean, after seeing all this information, empirical data, what is the most likely mechanism?
So,
You want to answer and
No,
that'll be the final.
okay, you answer,
Okay.
and that will be the final, and then we hold your questions, because we have a lot more information and discussion time, and.
For SPH simulations that we have run so far, we can only model the accretion, the jet launching compared to the mass accretion rate. I don't know. I know we have very well characterized the jet, its precision, but I don't know the mass loss rate particularly. I don't know, maybe radio astronomers do. And we can compare that to the mass accretion rate. But simulations, we can predict with everything you said, the X-ray emission, for example, which is telling us the mass accretion rate. But the jet in particular, the launching, I have no idea.
They don't know how to form the solar wind.
Solar
Not to form.
Can we stop?
Yeah.
Yes, otherwise there's no lunch, but hold your questions, there's gonna be a lot more opportunity